Welcome back, everyone, to the final talk of the Sophia track. With us right now, we have Guy Royse from the US. How are you doing, Guy?
I'm doing good. How are you doing today?
Fine as well. So Guy is a developer advocate at Redis Lab, and he's going to bring us a very esoteric talk because he's going to bring us a talk on understanding probabilistic data structures with 100 plus UFO sightings. So without further delay, Guy, you have the stage or the stream in this case.
Excellent. Well, thank you very much. Yeah, so welcome. Can you all see my screen?
Yeah.
Sharing properly? Okay, excellent. Excellent. So welcome, everyone. As Daniel said, my name is Guy Royse, and my talk is Understanding Probabilistic Data Structures with 112,092 UFO sightings. And yes, probabilistic is hard to say. So I will probably mess it up several times in the talk, even though I've given this talk probably about 40 times. So please bear with me as I fumble through the idiosyncrasies of the English language. This is a little hello, this is me slide. The key things on here is like, hi, I'm Guy Royse. I'm a developer advocate at Redis Labs. You might have heard of Redis. You might not have heard of Redis Labs. Redis Labs is the company that is sort of the home of Redis. We fund a lot of the open source development of it, and we've got commercial versions as well. And so that's my little advertising section, and that's done. The thing that I actually want you to look at here is my Twitter account. Please give me a follow if you like this content afterwards. The thing that you probably care about is the GitHub link where all of my code and slides will be at. So when the talk's done, you can go to github.com/Guy Royse and play around with this code and this tech yourself. So with that, done. 112,092. That is a big number. That is a surprisingly big number. It is the number of UFO sightings in this wonderful, wonderful data set put together by this man named Timothy Renner. And he didn't put the data set together. The National UFO Reporting Center or Research Center put it together here in the United States. He screen scraped their website with a bunch of Python code and got 112,092 of those records. And then he used them to do data science. What kind of data science did he do with them? Well, he did some clustering to find out where they tended to happen. And it turned out that the UFO sightings tended to happen near US Air Force bases. So guess it was the Air Force after all. The other thing that he found out was that he took the days of the year that were most common for UFO sightings. And the day that had the most UFO sightings in the United States was the 4th of July, which is our Independence Day. And so, you imagine a family sitting out there getting ready to watch fireworks and say, is that a firework, Dad? No, that's a UFO. That's a UFO. Definitely UFO. Yeah. So it was kind of stunning to see the chart because it was like the histogram shows like an order of magnitude increase in the number of UFO sightings on the 4th of July. So we're going to use this data to talk about probabilistic data structures because it's fun and it's kind of ridiculous. The data looks like this. It's just a CSV file. It's got some fields in here. We've got a summary of the sighting. This is sort of like a couple sentence short version of what that sighting was. In our case, 3 saucer-shaped ships. It's easy for me to say. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. So this is our little summary. We've got a city and state. This particular one happened in Salem, Oregon. It's got a date time. This one happened on September the 15th of 1950. It actually even has the time zone in there so we can see that daylight savings time was in effect at the time in Salem, Oregon. The shape of the UFO sighting is a disc. So you got like disc and light and, cigar and tic tac and all those sorts of things. How long it was, the link to the actual sighting on the New Forks website, the full text of the site. So this is the full eyewitness account, and then the latitude and longitude of the city. And so you can see there'd be a lot of fun data sciencey things you could do with this data. We're going to use it to explore probabilistic data structures. And so you're probably asking yourself, what the heck's a probabilistic data structure? If you are, you should not feel bad at all. Hopefully that's why you attended this talk, because you said, this is a thing I haven't heard of. I want to learn about this. Or I've heard of them, but I don't know how they work. That would be another good reason. But don't feel bad if you're not familiar with probabilistic data structures. I did a super scientific survey on Twitter, Whopping 119 people participated back in December of 2019, and 58%, 3 out of 5, had never even heard of them. And I have a lot of developers that follow me more than non-developers, so we'll assume that all 119 of these are developers. 1 out of those 5 had heard the term. However, I suspect a good percentage of those had heard the term in the very tweet asking them the question. And so I kind of lump them into the same category. The other 20% is split kind of evenly between they knew what they are or they've used them. And so odds are good you're in the 4 out of 5 category, not the 1 out of 5 category. So no problem. You don't know what a probabilistic data structure is. I didn't know what they were until about, I don't know, a couple of years ago. And here I am brazenly speaking on them. So to understand what a probabilistic data structure is, we need to first look at their evil opposites. The goateed Spock version of probabilistic data structures, the deterministic data structures. These are the data structures that, well, we already know and love. It's the ones we use all the time. So it's the lists and the arrays and the hash tables and the queues and the stacks. And these are deterministic data structures because they do predictable things. They do what we expect them to do. If I put something in a list and then I go look in the list, that something is in there. If I put something in a hash table, it's in the hash table. As opposed to probabilistic data structures, which sometimes will report falsehoods. It can have false positives and false negatives. They can lie sometimes. They have a probability of being correct. The thing you put in there has a probability of being there, which sounds a little insane. Like, why would I want a data structure that doesn't always store the things I put into it? But there are good reasons, and I'll get into them in a moment. But I want to actually dive deep into how they work. And so to do that, I want to talk about a deterministic data structure first, and that's the good old-fashioned hash table. You've used hash tables. If you took a data structures class in college, you've probably written hash tables because that's useful. You don't need to write hash tables anymore because they're baked into every language you use. If you're a JavaScript developer, a hash table is, well, pretty much everything in JavaScript. It's an object, right? If you're, as a Java developer, these are hash maps, right? It's just a key value store. For the key city, we get the value Salem, and then we can change that value. We can retrieve that value. We can set that value using that key. So we've all used the structure before. And some of us have probably thought a little bit about why it might be called a hash table. And that's because it makes use of hash functions. And you've probably encountered hash functions. You are probably familiar with them. You are probably thinking a hash function like SHA or MD5, the less secure version of SHA. But these, and those are hashing functions. And what they do is they take a numeric seed. Right here, I have a billion and some. I got a really big number here as a seed. And they take data. Here I have the bytes representing the UTF-8 encoded string for Scully from the X-Files. And it will take that data using the seed and will consistently smush it down into a number, a 32-bit number or a 64-bit number or 16-bit number, whatever you need. And it's a way of sort of like getting a fingerprint or a signature of the contents of that file. So you could have just a little bit of data. Here we've got 6 bytes, or you could have a 2 gigabyte video. You run it through the hashing function, and it's going to give you a single number, a single integer. And so that's what hashing functions do. The cryptographic hashing functions that you are more commonly familiar with are designed for security more than performance. For a hash table, you wouldn't want to use one of those because they'd be slow. You want your hash tables to be fast. And so you would use a hashing function that would be optimized more for speed than for security. In some of my examples later, I use a murmur hash. But the idea here is this hashing function sort of compresses down the data to a single value. A hash table takes advantage of this capability to generate the indexes used to put things into them. So your hash table consists of an index here. It's an array. It's an array of buckets. It's actually an array of linked lists, depending on your specific hash table implementation. And here I've got 10 items in my array because it fits on the screen and because it makes the math easy. And so when we add something to a hash table, we're going to add things to these buckets, and we determine our index by taking our city, our string, our key that's going into the hash table. We run it through a hash function, and we get a number out. And then we divide that number, we modulus that number by the width of our index, how many values we have in our index. So 0 through 9, we get 10. So modulus 10 gives us a number for what index to put it in. And this is really advantageous because this becomes a constant time operation. So regardless of where I'm going to put this in the hash table, it goes straight there, and then I can set the value. So here I put city, I get something that ends in a 1, so I put it in index 1, and that's gets Salem. If I add another value to the hash table, I get another index. So I put in state, and I get something that ends in a 4, and so I shove Oregon into index 4. But sometimes you'll get a collision. So here I'm entering shape, and I again get something that should go in index 1. And so in the case of a hash table, what we do is we have a linked list here, and we just add it the shape of that UFO sighting to the next item in the linked list. So when we go to read it, we just walk that list. So here we are reading city. City goes through the hash function, gets us something that ends with an index of 1. We look in position 1, and then we walk the list until we find the city, and city is the first one, so we return that value. So the hash tables use these hashes to generate these indexes into a fixed data structure. Now, hash tables can grow, and then we can resize them, and that is a process. But this is the core idea behind a hash table. We create a fixed array of linked lists and shove keys into it that way. So that's like hash tables in 3 minutes. Now, when we choose our data structures like hash tables or like linked lists, we're making trade-offs here. I kind of mentioned that city, this hashing operation and indexing, finding what our bucket is a constant time operation. It means regardless of how big our hash table is, it always takes the same amount of time to find that index. And that's a concern when we're choosing our deterministic data structures. What is the time complexity of operations on it? Is it linear? Is it go for every O of n? Is it for every item? If there's 10 items, it takes 10 times the amount of time, or if there's, is it the same amount of time every operation? And we're making these trade-offs both for time and space. So for example, a linked list is really compact. It's only as big as it needs to be. And so its space complexity is compact as it can be. It's O of n, but it's compact. Whereas its time complexity, if we want to find something in that linked list, we have to walk the whole thing. And by walking that linked list, that takes time. We could instead use a data structure like a hash table, which has constant time access, so it takes the same amount of time regardless. However, it tends to have a lot of empty space. It wastes space. You've got this array that isn't fully utilized. And so we're making these trade-offs when we pick our deterministic data structures between how fast they are and how much memory they take up. But this is actually a bit of a simplification because these aren't always in opposition. Because arrays, for example, have really good time complexity, but they're fixed. And so if you want to resize it, then it's hard. So the space complexity is more than just, the math problem of, is it linear, is it, logarithmic or whatever. It's also got sort of these nuances of just how they behave, and those are useful or not useful for us sometimes. And so many times we're picking them for those features as well. And it turns out there's a third thing that we can select on, in addition to how fast it is in certain scenarios or how much space it uses in certain scenarios. We can determine the accuracy of those data structures in certain scenarios. And this is to say, I could have a data structure that lies to me sometimes. I could say, is this thing in this set? And it could say, yes, probably. And you might be thinking, why would I want a data structure that lies to me? I want it to always tell me the truth. Well, that's fine until you've got 1 billion users. Let's say you need to pick a new username. I'm signing up for, Spacebook. And I need to pick a username, and they've got 1 billion users. And so how do they determine if that username's taken or not? Do they do select star from users where username equals username I want to use? Sift through 1 billion records and say, sorry, that one's taken. No, they're not going to do that. They're going to say, let's use some other data structure that will allow me to get a fast answer that doesn't take a bunch of space, and occasionally it will say a username's taken when it's not. It'll lie to us occasionally. But when you got a billion records, that 97% accuracy, perfectly acceptable. It's a trade-off. It's another trade-off that we can make, just like we can for space and time performance. And if you think about it, you've experienced these sorts of structures before. Strictly speaking, a JPEG is not a probabilistic data structure, but it is a little bit lossy, right? It compresses beyond the point where you can see it. Some of these pixels on the Devil's Tower here in Wyoming, made famous by Richard Dreyfuss and a pile of mashed potatoes, are not the right color. They're off, but it doesn't matter. It's good enough. And that's the idea behind a probabilistic data structure. They're a little bit lossy, but they're good enough. They meet our needs and give us improved performance and improved storage capabilities at scale. So that's the idea behind a probabilistic data structure. A lot of probabilistic data structures can be thought of as sets with particular properties. So a set, if you're thinking of set theory in mathematics, you've got, you can do intersections of sets, you can do differences, the whole Venn diagram thing, that sort of set. A probabilistic data structure is often a set that has a subset of its operations available. So here we've got a simple set, which is made up of the shapes that are in the Redis logo. That's a little bit of product placement there for you. Thank you. And I'm going to use that as an example here of some of the operations you can do. So you can ask a set to test for membership. This is saying, is this thing in the set or not? So is the square in the set? Yes, it is. Is there a pentagon in the set? No, there isn't. That's membership. So that's one thing you can ask a set. Another thing you can ask of a set, oops, wrong direction, is for its cardinality. This is the number of unique things in the set. How many unique, distinct type of items are in this set? Here we've got a star, a square, a circle, and a triangle. So we've got 4 unique types of things in our set. That's the cardinality. We can get the frequency of a set. The frequency is the number of the count of each of those unique things. So how many stars, how many squares, how many circles, how many triangles are in that set. And so this is, we want to count things. This is, you will use a probabilistic data structure that deals with frequency. Related to frequency is rank. Here, the idea is I want to rank the counting of things, but I don't care about the exact numbers. I just care, the first, the second, and the third place. Who's in first? If you ain't first, you're last, right? So rank can tell me that. And so it lets me hash down the data a little bit so I don't have to have super accurate counts. I just have to have relatively accurate counts using, if I just care about the rank. And then another thing we're going to look at here is similarity. Sets can be compared to each other to see how similar they are. And there are data structures that facilitate this to make it more performant. When it comes to probabilistic data structures, there's a lot to choose from. We're going to talk about 3 of them today. They're highlighted in blue. There is the Bloom filter, there is the heavy keeper, and there's MinHash. The little red daggers here are ones that that are part of Redis or Redis Bloom, which is a module that extends Redis to give it additional probabilistic data structures. A hyperlog log is in just Redis open source, vanilla, nothing added on. The others are part of the Redis Bloom module. But we're going to talk about these in detail: Bloom filters, heavy keeper, and MinHash, which do membership, rank, and similarity respectively. So how about we get into those and see how these things work? So the Bloom filter. A Bloom filter can only allow you to test for membership. You can add things to a Bloom filter. Of course, you can add things to any set, but you can only test for membership with a Bloom filter. And a Bloom filter will say, no, this thing is not in the set, or it's probably in the set. It cannot say yes definitively. They are very fast. All the operations are constant time, O of 1, and they have a fixed size. However, once you fill them up, they will always say yes, which so you want to make sure you size them accordingly. Bloom filters are useful for the example I gave earlier of, hey, I need to see if this username is taken. You could put all of your usernames into a Bloom filter and then say, is this username taken? And it'll say probably. And then you could deny the use of that username to someone. Now, it's possible it's not taken, that's a false positive, but that just means that username never gets used. And the trade-off there is you get improved performance. Another thing you can use Bloom filters for is for deduplication. So if you've got a lot of data, you can just add that to the Bloom filter, and it will tell you whether it's seen it before or not. And so you can just keep adding your data to the Bloom filter, and it will report back, yes, this is in there. No, it's not. And that will allow you to find duplicate files and records with a margin of error. Bloom filter is made up of two main parts. You've got some hash functions with their seeds. Remember this from the hash table and early on. We've got these seeds feeding these hash functions. Excuse me. And then we've got a bit array. That is the fixed, it's got a fixed width. So when we create our Bloom filter, we say, hey, I want a Bloom filter that is 1,000 bits wide, or 20,000 bits wide, or in our case, 10 bits wide. And to add things to a Bloom filter, we are going to run numbers through these hash functions and then set bits. And so here we're going to try to deduplicate UFO sightings for our database. We may have seen some of these UFO sightings before. We don't want to have duplicate UFO sightings. So, we want to see if we've seen this before. This one is Megatron in the Bushes. It's a delightful story of a couple of men who were driving down a New Mexico highway, and they had to pull off to take care of necessary bodily functions. And in the bushes, they heard the sound of Megatron from the Transformers transforming. That sound that the Transformers always made. And so they freaked out and got in their car and took off running, took off driving down the freeway. And these lights chased them for like 60 miles. And I think they were probably high. But anyhow, they left this delightful story of Megatron in the bushes. And so I want to see if we've heard this story before. And so I can add this to the Bloom filter by running through those hashing functions. I will get a bunch of unique numbers. I will modulus those with the width of my bit array, which is 10 in this particular case, getting indexes, just like with the hash table. And then wherever I have a number, I got a 5, a 0, and a 6, I flip the bit to high. Boom, it's added. That's all you do. To then read from the Bloom filter and say, is Megatron in the bushes in this Bloom filter or not? I just run through that same process, and instead of setting the bits, I read them. And if they're all high, if they're all 1, if they're all true, then this is probably in the Bloom filter. And that's it. I've got a JavaScript implementation of a Bloom filter that's got, I think, maybe 40 lines of code, including spaces and everything, comments and everything. They're actually very simple data structures to code up. So that's adding to a Bloom filter. Let's add something else to a Bloom filter. We've got another UFO sighting here. I seen a UFO when I was about 13 years old. That one happened right here in Columbus, Ohio, although it wasn't me. And this is the actual grammar that was in the sighting, even though it is grammatically incorrect. And in here, we've got the same process happening. We're running that thing through. We're getting our numbers. We're modulusing them. And we got a collision. Right? 2 and 1 haven't been taken before. And so we set those to high, but position 6 is already high. It was set high from Megatron in the bushes. But that's fine, because when we go to read this, we'll still get all 1s back. And when we go to read the other one, we'll get all 1s back. And they overlap a little, but they don't overlap entirely. And this is why we have multiple hashing functions, so that when we have this collision, the impact of that collision is not as negative to the outcome. It doesn't make false positive. The impact is less significant. However, it does increase the likelihood of a collision, and so we need a wider bit array. So there's a trade-off there with the number of hashing functions and the width of your bit array and the impact of any collisions. But so far, everything's fine. I can ask it if it's seen both of these, and it'll say, yes, I've seen both of these, and they will be true. They will be true positives. But you can also add sightings that will totally collide with all the bits. So here we have investigators from the Bigfoot Field Researchers Organization who have observed a glowing green-blue sphere. And here we get different numbers than the previous two examples, but it overlaps with all of them. And so if we add this, the Bloom filter doesn't change. And if we go then ask, was this added to the bloom filter? Is this sighting in the bloom filter? The bloom filter will say probably. And because as far as, if we added it, then that would be true. If we hadn't added it, then that would be a false positive. But regardless, there's a probability that this is a false positive. We don't know. And so this is why it's called a probabilistic data structure. The order that we added these things could have changed this outcome. If we added this first and added Megatron into the bushes, then I seen a UFO would have been a false positive, maybe. So probabilistic. And so the sort of the number of hashing functions and the with this thing, you're probably wondering, how do I figure out how to pick these numbers if I'm going to build one of these structures? Well, you just use this easy math. It looks intimidating, but it's actually really not that bad. You can use this in sort of a brute force way where you can say, I know I've got a number of items I want to store, and I've got I want to store about a million items. And I'm going to guess that that's going to take 10,000 bits. And then you use this second equation down here and solve for K. Then once you've got K, you solve for P, and they say, is this false positive rate acceptable? If it isn't, change the number of items or change the number of bits and in the appropriate direction and recompute. And so that is a way that you can get those values for you. Or you can do some trial and error. That works too. And there's actually an online calculator that will determine this for you as well. That's even easier. So, and of course, the easiest way is you can just use Redis. Right? Yeah, you can say call bf.reserve, which will set up a bloom filter, give it a key, give it an error rate. So here I'm saying 0.5% is acceptable. I want a 0.5% false positive rate, and I'm planning on putting 100 things in this bloom filter. To use it, you can just add things using bf add. And so it's bf add, the key name that we're using in Redis, and then the particular value we want to add. So here we're adding shapes of UFOs, disk, light, and here we're calling BF mad, which is the multiple add for light and teardrop. One interesting thing here that I think this is kind of neat is that it returns a 1. But down here we get a 0 back. And that 0 is because light was added before. So Redis will tell you when you add something if it's been added in the past or not. So if you're doing deduplication, this would be an easy way. Just add it. And then if you get a 0, you know it's not a dupe. If you get a 1, you know it's a dupe. So it's telling you whether the bloom filter has been modified. You can also query it explicitly with bf exists by passing in the shape and the key and the shape here. So disk and lights, they're both going to return 1. Triangle is not added, so that returns 0. So it returns 1s and 0s. Pretty intuitive there. So you can also just use bloom filters in Redis. They're fun to code up. I've got one here. I don't usually do this, but I'm going to show you the source code for a bloom filter. Let's see if I can. Looks like I can't get. There we go. So here's the bloom filter that I coded up in JavaScript. So up here, I'm bringing in a murmur hash. I've got a little bloom filter class. Here's the constructor, which is just saying how many bits wide does it need to be, and how many hashes do we want to use. I do a little validation. I create a new bit array. Now, this isn't JavaScript, so it's not an efficient way to do a bloom filter. I'm literally having an array of Booleans. I should really be doing bit twiddling here. But I create that array of Booleans, fill it full of falses. I've got a hash here. I create my hash. I create a new array with hash count. I fill it with a really big number. I create a random number. And then the last line here is creating a hash of functions that will hash given a particular value string. Then the only real lines of code here are these right here. This is the entire code for the bloom filter once we've got it set up. I can compute the hashes. You give it a string. I just walk over the hashes and then call the hash function for that string. And I then modulus it with the size. That gives me the indexes. And then to add, I just set all the bits. It's not particularly complicated. And here to check, I just check all the bits. And so I'm just doing basic array manipulation here. So we've got 44 lines of code and some of these are fluff. So very simple, little lightweight. They're not hard to code up. They're actually a lot of fun. So that is a little implementation of the balloon filter there. So balloon filters. We got, what do we got next? We got MinHash. So I'm doing okay on time. I got time. Good. So MinHash is a way of comparing documents. So I've got the little phrase here, determine set similarity between documents. And really the key word here is set similarity. How do we determine if sets are similar or not? And then if we're going to do set similarity between documents, there's a corresponding question, which is how do we turn a document into a set? And so let's look at these questions. Spoiler alert, we're going to use MinHash. MinHash uses a Jaccard similarity, or you can use Jaccard similarity after MinHash. Jaccard similarity is how you determine that set similarity. So here we've got Sculder and Molly from almost from the X-Files. And I've got sets for the states in the United States in which they've seen UFO sightings. So Sculder has seen UFO sightings in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio. And Molly has seen them in Florida, Kansas, South Carolina, West Virginia, New Mexico, and Ohio. And so Jaccard similarity is we take those two sets and get that intersection. We take the cardinality of the intersection. That'd be the number of items in the intersection. So New Mexico and Ohio, cardinality of 2, and divide it by the cardinality, or the number of items in the entire union of those two sets, which is 10. So these two sets are 0.2%, or they're 20% similar. They're 0.2 similar. If the sets were identical, we'd have 10 divided by 10. If they were not, and that would be 100%. And if they were not similar at all, we'd have 0 divided by 10, which would be 0%. And so this is a real simple computation you can make on sets to see how similar they are, which is cool, right? So you could take documents then and turn them into sets, and you could, do something similar. But how do you turn a document into a set? One naive approach might be to say, well, I'll just take all the words and put them in a set. But all that would really determine is what language the document was written in, because we're using all the same words. So you got a bunch of English documents, they'd all have they'd have a high similarity because they're all written in English. And so to avoid that, you can use a process called shingling, where we can turn a document into a set of trigrams. So what we do with shingling is we take this document and we take the first 3 words, a trigram, and that becomes the first item in our set. We take the next 3 words, not the next 3 words, but the overlapped next, not the overlaps next set of words. So they overlap like shingles on a roof, which is why it's called shingling. And so here we get, we notice 2 and notice 2R and 2R left. And we just go over the entire document all the way down to a bright glow at the bottom. So we notice to our left, further off in the mountains, a bright glow. And we've got a set of all the trigrams in that very small document. And then we can compare those sets and get a more accurate number. So instead of just having all the words in a language, we're saying how similar is Sculder's report here to Molly's report. And we can see that if we count them up and do the math and everything, we see that they're 63.6% similar. So Skinner looks at this, sees the reports, sees the Jaccard similarity, and is happy. But there's a problem with this as well, which is that we're doing a bunch of string manipulation, right? This is slow. If we need to compare, say, lots and lots of documents to each other, say we want to look for plagiarism, or say we're a search engine and we want to say, should we crawl this document again? Should we index this document we crawled? How different is it from the last time we indexed it? We can, we would want to do this on a lot of documents. And that would be really slow if we're just doing string manipulation. And so you can take these sets of shingled, this document, these shingled sets, and you can do a MinHash calculation against them to turn them into hashes. And the way that works is you go through, and again, we're doing hashing functions. And so we've got a set of hashing functions. I have 3 here. I would recommend more, but I'm using 3 because it's convenient. It fits on the screen. And for each hashing function, we go through the entire set. So here we've got we notice 2 goes through the first hashing function, giving us 325. 2R, notice 2R is 489, all the way to the mountains A of 312. And so we go through the set, we create a set of numbers, the hash of each of those trigrams. And then we create multiple sets, one for each hashing function. And so now that we've got these sets, we create a new set over here on the right. And this set is made up of the minimum number in each of these sets. So this is 233, this is 143, this is 102. And so we get a set of 3 numbers. And then this is sort of like a signature of that document. And we can compare that to another document. Here we've got Molly's report. We get other numbers. When we hash everything, our minimum numbers, the minimum of all those hash numbers, gives us another set of numbers, and we can compare those. We can say, what is the Jaccard similarity of this set of numbers from on the left from this set of numbers on the right? And this becomes a function of our number of our hash functions that we used. But in this case, we can see that these 2 documents have a similarity of 0.5, so they're 50% similar. That is not quite as accurate, or I should say finely grained, as quite as granular as the previous result, but that's because I only picked 3 hashing functions. If we wanted more resolution, we might want to do 10 or 20 hashing functions instead. And then we can compare these sets. And so, but at that point, then you're doing that same Jaccard similarity calculation. You're just doing it on the MinHashes, the minimum hashes, as opposed to the actual documents themselves. So I think this is kind of cool. I do have coded samples for that. I'm not going to bring them up, but you can check them out on my GitHub later. The last data structure we have is called top K, which is a combination of 2 things. It's heavy keeper, which is the thing that's is honestly the interesting part, with a min heap. Top K is all about ranking. It can count as well, but its counts aren't reliable, but it's good at ranking. So it'll tell you what are, for example, the top 10 IP addresses that my traffic comes from, or what are the top 5 most commonly used words in UFO sightings, which is the example we're going to, the example I'm going to show you at the demo at the end of the talk. And so top K is all about ranking your top K items. So I've got, what are the top 5 most clickbaity words used in UFO sightings? That's the thing we're going to find, right? 2 parts, the min heap and the heavy keeper. And the heavy keeper is, well, it keeps the heavy things. It keeps the things that come in more often and tends to throw out things that are less common. Heavy keeper is another one of these hashing structures. We're always using hashes to sort of eliminate, to sort of like hash the data down, to boil the data down to numbers. We have in here, we've got a height or a depth, which is the number of hashing functions we're using. You can use as many as you want. And you've got a width, which is how wide the buckets are. Now that's, and we're going to use, we're going to hash, values into here, and those are going to determine the index for those buckets. Each bucket has a place for a hash value and a place for a count. A brand new heavy keeper has nulls and zeros for their hashes and counts because there's nothing in them. When we go to add something to a heavy keeper, I'm going to add popular UFO shapes so we can rank different shapes of UFOs, how popular they are. So if we add the value for object, which is in the top 10, that's like, what shape was it? It was an object. It's like, we're in JavaScript again, aren't we? Then the object as a string is passed into those hashing functions. We get a number out again. We modulus it with the width of our buckets. And then we get an index, just like we've been doing on all these other data structures. That index, we look in there and we say, is that index got anything in it? Is the hash value populated? If it's not, which in our case it's not, then we put our hash value in there and we set the count to 1. Hey, we added object. Now, position 2, position 1, and position 2 are taken. We populated the hashing values. We've got our count. Great. If we add the word object to it again, it gets the same values and finds the same positions, but this time the hash function, the hash property on the bucket has a value in there, and they're the same. And since they're the same, we will increment it. So now we can go in there and say, oh, there's 2 items. And now if we want to go in and query the count, we just go through that same process again. And instead of writing things, we read, and we say, hey, what's the count for object? And we'll go to each of these and we'll get a 2, a 2, and a 2. We'll take the lowest or the largest one of all of those, which is a 2. But it won't always be a 2. They can go down. But we'll take the largest value of those and then return that and say, hey, there's 2 objects in here twice, which is correct. If we want to add something else to our heavy keeper, let's use the word light, another popular word in UFO sightings. Here, we get different hashes and different indexes. And so we, in the first and second row, we populate different places. But in the third row, we have a collision. The hash values are different, but the index is the same. So what do we do here? It looks and says, well, these hash values aren't the same, so I can't increment. What's the correct course of action? Well, there's a probability that the number will be decremented, that will have decay. And that probability, if it bears out, we will reduce that count from 2 to 1. That probability is determined with this formula. Probability is equal to B, which is a number we select that is greater than 1, but also around 1. So like 1.5, 1.05, or 1.1, or 1.01, or something like that. To the power of the negative count, that's the 2 in our example. If the count was 1,000, it would be negative 1,000. And so 1.05 to the power of negative 2, once we do the math, comes out to 90.7%. So there's a 90.7% chance that we'll decay. What's interesting here is that the bigger the count, the higher this number, the smaller the probability. So if this is 1,000, we're going to hang on to it. It's the probability to decay is greatly reduced. Whereas the small things are easy to decay. So things that don't have very big counts can get reduced to 0 and be eliminated from the heavy keeper. Things that have high counts are harder to dislodge. That's why it's called a heavy keeper, because it keeps the heavy stuff and throws away the light stuff. And if you think about it from a desire to rank things, keeping track of the top 10, the heavy stuff, is what you want to keep track of. So we've got a 90% chance, over 90% chance of decay. So we roll the dice, and let's go ahead and say that decay happens. And so we leave this hash value the same. This is still tied to object. It's not tied to light, but the value in count is decremented by 1. So this is what our heavy keeper looks like now. Now, if we go and query the word light, it finds matches in the first 2 rows, but in the third row, it doesn't find a match. It finds the index, but the hashes don't match. And so it looks at the 2 rows that work and says, well, what's the maximum value? It's 1. Great, we'll use that one. And for object, when we go to query object, it finds 2, 2, and 1 as the counts back now. But it returns the max, and so it returns 2, and so this still works. And so much like the Bloom filter, this redundancy allows it to be tolerant of the hash collisions. And that's pretty much how a heavy keeper works. Now, the top K, what it does is every single time you add something to this and you get the count back, it adds it to our min heap. And it looks at the value here, the object 54, for example, and says, is my count that I just got by this thing I added greater than what I have in place already? No, throw it away. Yes, put it on the heap and resort it. And so the min heap will then we can then ask the min heap for quickly to get our top 5 items. So we're using that min heap and that heavy keeper together to make a nice efficient little data structure. Redis supports top K. You can create an object with the command topk.reserve, pass in a key. You can say how many items do we want to keep track of? The top 3 things. How big is my min heap? How wide is that structure? How deep is that structure? How many hashes? And the decay rate here is Redis uses the reciprocal of that number that I used in the formula. So this is so it'd be 1 over 1.05, whatever that works out to be. To add things to top K, we just say top K.add, give the key name, and then the things we want to add here, we're adding disk and teardrop, light, disk, and teardrop. So that's 3 disks, 2 teardrops, 1 light. And if we want to query it, we can say, is disk in the top K? So is top K.query disk? We'll say, yes, it's in the top K with a 1, or 0, no, it's not. We can get the count. The count's not super reliable. It gets battered as a part of this decay process. So it's not the super reliable number. It's guaranteed to be not larger than reality, but it's probably going to be smaller than reality. But you can query that. And then you can also get the top K list and just ask it, give me the top K, and it'll spit them out. And that's using top K and Redis. I've got a fun little demo that I put together. I think I've got time for it. I've got 5 minutes, right?
Yeah, we still have a question or two.
Oh, sure.
But that's fine. Go ahead and show us your demo, because
Okay.
I'm actually curious right now.
Okay, so I've got this fun, ridiculous little demo. It's I apologize, it's in Python. I just got some hate for Python. So it's a little bit of code here, but what it does is it uses Redis's top K. And I use Python because I had access to NLTK, natural language tools, and pandas, and so I can read in this, and I can use NLTK to get rid of stop words, so common words in English that would be not meaningful, like a, and the. So, but to kick this thing off, I can say Python app.py. I've got a little app here that's going to go through this big data set of UFO sightings and count them. It's going to pull it constantly. So right now, those are from a previous run, but it's going out and it's just asking Redis, what's the count? What's the count? What's the count? What's the top K? What's the top K? What's the top K? And then here we've got build.py. Build.py is going to go through and read the CSV file, which has got all of those sightings in it, one at a time, and just start adding them to Redis. So here we go. So there it's going. It's reading those files, breaking them into their words, getting rid of the stop words. And we can see it is updating about every second here. And you can see the lists are changing order a little bit. You see lights and light are popular words. Object is popular here. It's in the top 3. For UFO shapes, we've got light and disk and triangle are popular shapes. And this will run until it goes through all 112,092 of them. So this is my fun, ridiculous little demo using Redis top K to parse through this UFO data. I don't want to go into the code too much because I'm cutting it a little close to the line, but let me go ahead and there was a question. I can take a question here. I got some links here. Just a lot of the resources I used here. And here's some Redis links. If you have questions about using top K or using Bloom filters in general, I'm always on the Redis Discord server, so you can ask me there. But I'll leave this up so that you can get these slides and get all those links. Just scan this QR code. I promise it won't rickroll you. And I'll go ahead and answer the question real quick.
That's fine. Actually, that's a great way to present data structures. It's actually because some of the questions we actually had were on the data set. So on your actual data on UFOs, I answered those questions the best I could. But
Excellent.
we now have a question by Garden State's Java user group, which asks, is it fair to say that hashing is the fundamental tool in probabilistic data structures? It seems like a natural use for hashing.
Yes. I mean, the short answer, yes. I think that's a very fair thing to say. Every probabilistic data structure that I've dived into uses hashing functions of some sort. Too many SHs in all these words. It's Sioux sells seashells by the seashore, right?
Yeah.
So yes, I think that's a completely accurate thing to say. That's sort of the essence of it, is you hash these values down to numbers and then store those numbers in interesting ways.
Yeah, that was my assessment, yes, as well. But so we had a couple of other questions, but they were basically on first. The first one was these sightings, these 112,000 something sightings are only from the US, aren't they?
Yeah, the US only. I apologize for my US bias. It's the
No
data
worries,
set
no
I
worries.
have. Yeah. It's
I
about to get
wasn't
really exciting with all the stuff in the news lately, right?
so yes, and the other one was well, it was actually about the programming language that you were using for that particular example, which was JavaScript. But the question I had, which is usually close to every data science talk, is if you had to pick a language to treat data, what would it be? Just one.
If I have to pick a language for doing like data science stuff with data, Python's probably the go-to, simply because it's got the most mature tool set there. I know. But Pandas is pretty powerful. It's not necessarily about the language. I'm not like an enormous fan of Python. I'm kind of neutral towards it. It's just the tooling, right? The tooling's there, and so that's why it's the go-to.
That's great. Thank you once again, Guy, for the amazing talk. What an amazing close to of already long day. We are moving. The team is moving to the Aminium room. So if you want, you can join us there. It's just for a quick goodbye and thank you all. So thank you once again, Guy. Hope to see you next year. At this time at Coimbra, and not
absolutely. I would love to come.
Over some squares on Zoom. So thank you all.
I promise to bring whiskey.
That's always good. Thanks all that joined us today, and we hope to see you next year on site.